Hey guys, I'm going to do a short demo of the lab that we did in class or that I demonstrated in class. And this is for the folks that are not able to come in and can't see this. We'll do the best we can here. All right, we're going to start off with here we are. This is a um, illustration of a standing wave in a tube of air. So this is a standing sound wave. Now, as you know, a sound wave is a longitudinal wave in which the waves travel in the same direction as the energy. So uh, this one down here, this is a standing wave in a transverse wave, which we're more familiar with. They're easier to see. But as you can see in this, they represent each other here. The black one represents the dots. So the dots are individual air particles. And as you can see, this is an antinode where I have the cursor right here. That's where in a standing wave, the medium is moving a lot, moving up and down a lot. And then this is a node where the medium does not move at all in a standing wave. Okay, so the red dot here is an air molecule which is on a node in the standing wave from the sound, and it doesn't move back and forth at all. Whereas this red dot here is moving back and forth because it's on an antinode, so it's moving a lot. It's sloshing back and forth. Yeah, so it's just sloshing back and forth. Okay, so it looks sort of like an accordion, but if you look closely, you can see there are some places where the air molecules are not moving at all, and other places where they're moving back and forth a lot. And those are the nodes and the antinodes. Okay, so and we need to know this because we're setting up a standing wave in a tube of air. Now, we also mentioned before, I think, and if we didn't, I should at this point, that a standing wave actually is an example of resonance. We studied resonance last time. And when an object resonates, it oscillates rhythmically at a natural frequency, and the amplitude tends to increase as the resonance increases. So a small vibration can induce a very large oscillation in something that is resonating. And the standing wave in this pipe, this closed pipe, that air is resonating. Now, one more thing to see. This is an open end, so this is open to the atmosphere outside, and this is a closed end over here, which means that the air at the bottom of the tube can't move because it's touching a rigid surface, which also can't move. So that means that at the bottom of the pipe, there's a node, and we can see that on this diagram here. This is a node. The air molecules are not moving at all. Now, conversely, up here at the mouth of the tube, we have an antinode, and the air is moving back and forth a lot. And that means that that air can move the air out in the room, and we're going to be able to hear this resonance because the air is oscillating back and forth at the mouth. That oscillates the air, forces the air in the room to vibrate, and we perceive this as sound. Okay, so that's two pieces we've got. One, that the air in this tube is resonating, and it's a standing wave with a node at the bottom of the tube. Okay, so these are the requirements to have a resonance of air. We have to have a node at the bottom of the tube and an antinode at the mouth of the tube. And if that's the case, then we have conditions right to have a standing wave and a resonance in there. Now, we often represent sound waves as transverse waves because it's just easier to draw pictures up. But this diagram right here, this shows the first time that a tube of air can resonate. Remember, we have to have an antinode at the mouth and a node at the bottom of the tube. And the first time we can do that is with this formation here. We have an antinode and a node. And if you look closely, you can see this is 1/4 of a wavelength. Okay, this is 1/4 of a wavelength. What do I mean by that? Because a lot of people say, hey, wait, that's a half wavelength, Mr. Robinson. No, it's only 1/4 of a wavelength. So let's look at this one down here. And we're going to look at these two lobes that are close to the bottom. So we're going to ignore this bit of lobe out here. We're just going to look at these two lobes right here. This is a full 1 wavelength of a standing wave, because when this is a trough, this is a crest. And then when they switch, then this becomes a crest and this becomes a trough. So one full cycle is going to be a crest and a trough, or a trough and a crest. So this is a full wavelength. And this here, this single lobe, this is a half a wavelength, which means that this up here is 1/4 of a wavelength. Okay, so 1/4 wavelength is when air can resonate in a tube of air. Why does this matter? Well, I'm going to give you the last piece here, but I do want you to remember that 1/4 wavelength is important. So why do we care about this stuff? Because we're going to use the wave equation, which, as you know from doing your review packet, is an important thing that you have to know. So V equals lambda F, that is our wave equation. V is the wave speed in meters per second. Lambda is the wavelength in meters, and F is the frequency of the wave in hertz, which is cycles per second. Okay, and really the wavelength is meters per cycle. Okay, so what we're going to do is we're going to figure out when sound is resonating, and from that we'll be able to measure the wavelength. And if we know the frequency, we can do some calculations here. Okay, so I'm going to show you something. This is a tuning fork. And yes, as you can see, the frequency of this tuning fork is 320 hertz. So we have a frequency of 320 cycles per second. Now we just need to figure out a wavelength. And we're going to do that by looking at this apparatus over here. All right. This is a column of water, but what we're really interested in is the air above the surface of the water, because this is a column of air. We might be able to make this air resonate. Okay, now you can't really see it from here, but there's a meter stick which is taped to the side of this, so we can very precisely measure how long this column of air is. Now, I'm going to ring the tuning fork, 320 hertz. Even I can barely hear it, but listen. I think for a moment you were able to hear that it got loud before the sound canceling in the software made it go away. It rings, and it rings at this 320 hertz frequency. It sounds like an organ pipe. You can hear it very clearly in the classroom here. Now we know, because it's ringing, that the air is resonating in this tube. And that means that the length of the tube, which was 26.5 centimeters, that is equal to 1/4 of a wavelength, because the air resonates when we have 1/4 wavelength in the tube. So this means that 26.5 centimeters is 1/4 of a wavelength. So that means that 26.5 centimeters, the wavelength is 106 centimeters, or 1.06 meters, and that is equal to lambda, the wavelength. So we can put that in here, 1.06 meters. So what, Mr. Robinson? Well, when we multiply these together, 1.06, and we divide that by 100, so we have meters, 1.06 meters, times the frequency, 320, we get 339, 340 meters per second. And that is the speed of the wave, which in this case is the speed of sound. The speed of sound. So we were able to use that apparatus that you saw just a moment ago and a tuning fork to calculate the speed of sound, which is pretty amazing because we can't see sound go through the air, and it goes too fast for us to see even if it was moving. And yet we're able to use this equipment and the wave equation to determine the speed of sound in our lab, which is pretty cool. Okay, so this is something that you need to be familiar with, how we did it, how we recognized that it was 1/4 wavelength within the tube. We were able to measure that with the meter stick, multiply it by 4 to figure out the length of an entire wavelength. We combine that with the frequency of the tuning fork that resonated at 1/4 wavelength, and from that be able to find the speed of sound. Now, if we'd used a different frequency, we'd get a different length, but we'd still get the same speed of sound. Okay, I think that's about all the time we have, so we're going to stop it there, and we will see you next time.